Good morning, students. Today we are going to discuss about P block elements. There, the first group we are going to discuss in P block elements. First part is group 13 elements. Group 13 elements. Now, what are group 13 elements? Let us see. The group 13 of the periodic table, it has the elements boron, aluminium, gallium, indium, and thallium. Boron, aluminium, gallium, indium, and thallium. Here, boron is a non-metal, while aluminium and other elements of this group, they are metals. And we know that down the group, as we move down the group, that is metallic character increases and non-metallic character decreases. Here, boron possesses properties which are different from the other elements of the group. And due to its small size and high ionization potential value, boron, it shows diagonal relationship with silicon, that is the second element of the fourth group. And let's discuss about the different general characteristics of third group elements. Third A group elements have 13 group elements. Okay. Now, there the first one is occurrence. Here, boron, it never occurs free in nature. That is, it is not available in the nature in the free state. That is, it is available in the form of compounds. That is, it is always found in combined with oxygen. Okay, so boric acid is found in the jets of steam and in certain volcanic regions, and stinkal, that is Na2B4O710H2O. This is sodium, we can say that it is a borax. And other minerals include ternite. This is the formula Na2B4O7 4H2O. Tinkal is Na2B4O7 10H2O, and ternite is Na2B4O7 4H2O. Calamanite is Ca2B6O11 5H2O. And boracite is magnesium. This is Mg3B8O15 MgCl2. And another one is boronatrocalcite. Okay, boronatrocalcite. Ca B4O7 NaBO2 8H2O. So these are all the compounds of boron. So boron exists in nature in the form of its compounds. That is, mostly it is combined with oxygen. We can see here in most of the compounds, boron, it is combined with oxygen. Okay, so this is about the occurrence of boron. Next, aluminium. Aluminium is the most abundant metallic element and the Earth's crust. The most important one of aluminium ore is bauxite. Bauxite is nothing but Al2O3 2H2O. And gallium, indium, thallium are found in only small quantities in the nature. So indium occurs in all commercial samples of tin and in the mineral cylindrite from Bolivia. Okay, so thallium occurs in most forms of pyrites in zinc ores and in the mineral crooksite. So this is about occurrence of the elements of 13th group. Now let's see the electronic configuration of this group of elements. Okay, electronic configuration of this group of elements. Now the outer electronic configuration, if we consider these elements, they have Ns2Np1 electronic configuration. We can see here Ns2Np1. That is, they have 2 electrons in the s orbital of outer shell, that is the nth shell, and 1 electron in the p orbital of nth shell. Altogether, 3 electrons are present in the outermost shell of these elements. Okay, so boron and aluminium, they have noble gas core. Boron and aluminium, they have the noble gas core, while gallium and indium have noble gas plus 10 d electrons. Noble gas core in the sense N2 Np6 electronic configuration, while gallium and indium they have noble gas plus 10 d electrons. Okay, thallium has noble gas plus 14 f electrons plus 10 d electrons. In the case of thallium, N2Np6 and 10 d electrons are present, and 14 f electrons. 10 d electrons are present in n minus 1th shell, and 14 f electrons are present in n minus 2th shell. Okay, so the electronic configuration of the elements is more complex when compared to the alkali and alkaline earth metals. In the case of alkali metals, that is 1a group elements, the outer electronic configuration is Ns1, whereas alkaline earth metals it is Ns2. But here in the case of these elements, it is Ns2Np1. Now let us consider the electronic configuration of these elements. So 13th group elements electronic configuration. First element is boron, atomic number is 5, and electronic configuration is helium in the sense 1s2, 2s2, 2p1. So outer shell 2s2, 2p1, that is ns2, np1. So helium 2s2, 2p1, altogether 5 electrons are present in boron. Now let's consider aluminium. Aluminium atomic number is 13, symbol is Al, atomic number is 13, and electronic configuration neon 3s2 3p1. Neon is 10 electrons, it has 10 electrons, and 3s2 12 and 3p1 13. So total 13 electrons are present in aluminium, neon 3s2 3p1. Now let's consider gallium. Gallium Ga is a symbol given, and atomic number is 31, and its electronic configuration is argon 4s2 4p1. Argon 18 electrons, 4s2 20, and argon here 3d10 should be there. So argon 3d10 4s2 4p1. Argon is 18 electrons, 3d10 28, 30, and 31. Now next one is indium. Indium atomic number is 49, and its electronic configuration krypton 4d10 5s2 5p1. Krypton 36 atomic number plus 10 46 plus 2 48, and this one 49. So this is electronic configuration of krypton. And last one is thallium. Thallium symbol is Tl, and atomic number is 81. Its electronic configuration is xenon. Xenon 4f14 5d10 6s2 6p1. This is the n minus 1th shell. This is the n minus 2th shell. So xenon is 54 plus 14 is 68 plus 10 78 plus 2 80 and 1 81. So this is about the electronic configuration of this 13th group elements, where the outer shell has NS2 NP1 electronic configuration. NS2 NP1. Okay. Now another general characteristic of this group elements is atomic and ionic radii. Atomic and ionic radii. Okay. So as we move down the group, that is from boron to thallium, one extra shell of electron is added, and therefore an atomic radius is increased. Atomic radius is increased due to increase in number of shells as we move down the group. However, a deviation also can be seen. Okay, here and there deviation we can observe. So atomic radius of gallium is less than that of aluminium. Here you can observe gallium, it should be larger than aluminium, but it is less, we said. So atomic radius of gallium 135 picometers is less than that of aluminium 143 picometers. The reason is attributed to the presence of additional 10 d electrons, which offer poor screening effect. Due to poor screening or shielding effect of d electrons, the atomic radius of gallium is less than that of aluminium. Okay. Now next, ionization, potential or ionization enthalpy or ionization energy. So ionization enthalpy. This ionization energies or ionization enthalpy from boron to aluminium is associated with increase in size. As we move down the group, what happens? Atomic size increases. Therefore, ionization energy should be less. Okay, so the discrepancies in ionization energy values are found in between aluminium and gallium. Indium and thallium due to low screening effect of d and f electrons. So actually, as we move down the group, ionization enthalpy must be less or it should decrease as we move down the group from boron to aluminum. But here and there discrepancies are present due to various reasons. If we consider aluminum and gallium, there is difference in size. Because of that reason, the ionization enthalpies are also there is change from the trend. And in the case of indium and thallium, it is due to low screening effect of D and E of electrons. So this we have to remember in the case of ionization enthalpies. Otherwise, in general, in the case of S block elements, as we move down the group, what happens to ionization energy? It slowly or gradually it decreases due to increase in atomic size. Wherever there is a discrepancy in atomic size, there we can observe some change in the ionization enthalpies trend. Now, next one, let us consider electronegativity. Electronegativity is nothing but the ability of an atom in a molecule to attract the bond pair of electrons more towards itself. So here the electronegativity, as we move down the group, what happens? Let us see. Electronegativity, it depends upon the metallic and non-metallic nature. As we move down the group, what happens to metallic nature? Metallic nature gradually increases. Metallic nature gradually increases. Therefore, there should be decrease in the electronegativity. So, electronegativity first decreases from boron to aluminum and then increases marginally due to discrepancies in atomic size of the elements. So, general trend is as we move down the group, electronegativity should decrease. But here, from boron to aluminum, there is decrease. This is normal trend. And as we move down the group, that is from aluminum to thallium, what happens? It increases marginally due to discrepancies in the atomic size of the elements. And this discrepancy in atomic size is due to this screening effect. Low or poor screening effect of D and E of F orbitals or F electrons, we can say. Next one is electropositive character. Electropositive character. Electropositivity is nothing but metallic nature, and we have already said metallic nature or electropositivity, it increases down the group. It increases down the group. So electropositive or metallic nature of the elements increases from boron to aluminum, then decreases from aluminum to thallium. So boron to aluminum, it increases and then it decreases from aluminum to thallium. This is also shown by their standard electrode potential for the reaction. So that we can observe with the help of standard electrode potentials. Okay, so here let us see the tripositive ion, M plus 3 electrons gives rise to M. Okay, so the standard electrode potential E for M plus 3 by M reaction becomes less negative from aluminum to indium. So then it becomes positive in the case of thallium. So from the electrode potential values, that is E naught values, it can be inferred that we can see here. What are the inferences drawn from these values? So it becomes easier for the reduction, that is M plus 3 becomes M, that is addition of electrons is nothing but reduction. 3 electrons are gained by this ion to give this to occur on descending in the group. So this reduction reaction increases, that is ability to gain electrons increases as we move down the group. Okay, so the oxidation state plus 3 becomes less stable in aqueous solution on descending in the group. So ability to lose electrons, that is plus 3 oxidation state becomes less stable and plus 1 oxidation state stability increases down the group. So here we can see the oxidation state plus 3 becomes less stable in aqueous solution descending in the group, and plus 1 oxidation state becomes increasingly stable as one moves from boron to thallium. So thus with the thallium plus 1 state is more stable than plus 3. Thallium in plus 1 oxidation state is more stable than in plus 3 oxidation state. Plus 3 oxidation state, and this is due to inert pair effect. This is due to inert pair effect. So the electropositive character first increases from boron to aluminum, and from aluminum to thallium the positive nature decreases, and this change is corresponding to the changes in the atomic sizes. As there is discrepancy in the atomic size trend, because of that reason this effect we can see in the case of electropositive character. Otherwise, in general, in the case of S block elements, as we move down the group, what happens? The electropositive nature also gradually increases with increase in atomic size. But here there is discrepancy in the atomic size. Because of that reason, the electropositive character also there is some change in the trend. Next one is oxidation states. This 13th group elements, they exhibit plus 3 common oxidation state as they have 3 electrons in the outer shell. As their electronic configuration, outer electronic configuration is ns2 and p1, that is they have 3 electrons in the outer shell, their common oxidation state is plus 3. But the thallium, we said this is the last element of the group, it exhibits plus 1 oxidation state only due to inert pair effect. That is, the ns2 electrons which are present on the outer shell, they are inert to participate in bonding. Because of that reason, thallium is more stable in plus 1 oxidation state than in plus 3 oxidation state. And next one is density. Density from boron to thallium, it increases due to increase in size of the atom. Next, melting and boiling points, let us see. Melting and boiling points, they do not vary regularly due to structural changes in the elements. Because of the differences in the structures of the elements, there is no regularity of melting and boiling points of these elements. And boron has a very high melting point because it exists as a giant covalent polymer in both solid and liquid states. Because of that reason, it has high melting and boiling points, especially melting points, high melting points, because it exists as a giant polymeric state. And the melting point decreases from boron to gallium and then increases down the group. And the low melting point of gallium, that is 29.8 degrees centigrade, is due to the fact that it consists only Ga2 molecules, Ga and Ga2 molecules. It remains liquid up to 2000 degrees centigrade and hence used in high temperature thermometry. It exists as a liquid at up to 2000 degrees centigrade. Okay, so at about 29.8 degrees, and that is around 30 degrees centigrade itself, it melts and it becomes a liquid. So this is used in high temperature thermometry. Next one is reactivity. Reactivity. Reactivity with air, let us see. Boron, it is unreactive in crystalline form, and aluminium, if we consider aluminium, very thin oxide layer on the surface which protects the metal from further attack. That is, boron, it doesn't react with air, whereas aluminium, it forms a very thin oxide layer, that is a Al2O3 layer over the surface of the metal. Because of that reason, the metal, it will not be attacked by air once again. Once the oxide layer is formed. So amorphous boron and aluminium metal on heating in air form B2O3 and Al2O3 respectively. So this also forms nitrates with nitrogen. So in air, it contains nitrogen also. Because of that reason, these elements, when they combine with this air, then what happens, from the oxygen of air, it reacts with these elements to form oxides, and nitrogen of air, it combines with these elements to form nitrites. So these elements, they react with air on heating to form oxides and nitrites. Here E stands for element. So oxides of aluminium and gallium are amphoteric, and those of indium and thallium are basic. So boron trioxide is acidic. Boron is a non-metal, because of that reason its oxide is acidic. And aluminium and gallium, they have semi-metallic nature. Because of that reason, aluminium and gallium, they form amphoteric oxides, and indium and thallium, as they are metallic in nature, they form basic oxides. So metallic oxides are basic in nature, non-metallic oxides are acidic in nature, and semi-metals, they form amphoteric oxides. Aluminium, though it has high metallic character, it forms the oxide, that is Al2O3, which is amphoteric in nature. That is, it has both acidic as well as basic nature. Even gallium oxide also, it has amphoteric nature. Now, reactivity with acids and alkalis. with acids and alkalis. So boron, it does not react with acids and, and alkalis, but aluminium, it dissolves in mineral acids. Aluminium, if you consider aluminium, it dissolves in mineral acids and in aqueous alkalis. Therefore, it shows amphoteric nature. Boron, in the case of boron, it does not react with acids and alkalis, but if we consider aluminium, it has the capacity to react with acids, that is mineral acids like HCl, H2SO4, etc. And even it also combines with aqueous alkalis like NaOH, KOH, etc. Therefore, it shows amphoteric nature. Now, let's consider reaction of aluminium with acids. With acids, aluminium, it combines with acid, that is HCl. It forms AlCl3, releasing hydrogen gas. Al plus 3 C6 elements, that is AlCl3 plus H2, hydrogen gas. So the reaction with concentrated HNO3 is passive due to the formation of protective oxide layer on the surface. So when this aluminium, it combines with the another mineral acid, that is HNO3, then what happens? Nitric acid is powerful oxidizing agent. Because of that, it oxidizes aluminium to Al2O3. That Al2O3 layer is formed over the surface of this particular aluminium metal. Thus, it becomes passive towards further attack by HNO3. Okay. Now, next, let's consider the action of aluminium with bases. Aluminium, it reacts with alkalis like NaOH or KOH, liberating hydrogen gas. So, aluminium plus NaOH gives rise to NaAl. Here NaAlO2 we will get actually liberating hydrogen gas. So in this reaction, aluminium, it is reacting with alkali, and in this reaction aluminium, it is reacting with acid. So because of that reason, aluminium is said to possess amphoteric nature. Now, reactivity with the halogens. If we consider the reactivity of these elements with halogens, these elements, they react with halogens in the sense fluorine, chlorine, bromine, iodine, etc., to form trihalides, except TiI3, except this thallium TlI3. The rest of the triiodides, trihalides are possible. That is, these elements, they combine with halogens. Halogen in general, we use the formula X2. So these elements, they combine with the halogens to form the trihalides EX3. If it is BX2, BX3, ALX3, like that. Okay, E stands for element of this 13th group, and X stands for halogen, that is fluorine, chlorine, bromine, iodine, etc. So this is B. If this is F2, then we get BF3, BCl3, BCl2. Here BCl3, AlCl2, AlCl3, like that, AlBr2, AlBr3. Okay, next, compounds of boron. This is specific compounds of boron. Let's consider in this group. So, boron, it forms boranes. Now, what are boranes? The hydrates of boron are called boranes. Hydrates of boron are called boranes. So, boranes are simple boranes, compounds which have the molecular formula equivalent to BnHn plus 4, BnHn plus 4, where n equals to 2, 5, 6, 8, 10, or 18 are called boranes. So, boranes are hydrates of boron, where these boranes are classified into different types. There, the first one is simple boranes, and higher boranes also we have. Here we are considering simple boranes. In simple boranes, the general molecular formula of the simple boranes is equal to BnHn plus 4, BnHn plus 4, where n is equal to either 2 or 5 or 6 or 8 or 10 or 18. Okay, these are called boranes, and these are quite stable and hence more important. Now let's consider the first member of this simple boranes. See, the molecular formula B2H6, where n is equal to 2. B2H2 plus 4, that is 6. Here, B6, this one. B6 plus H, n, that is 6 plus 4 is equal to 10. This one, B10, H10 plus 4, that is 14. Here, B5, H5 plus 4, that is H9. So B8, H8 plus 4, H8 plus 4, therefore B8 H12. So here this is known as diborane, this is pentaborane, here hexaborane, this is 8 stands for octaborane, this is 10 decaborane. And here this number, it indicates number of hydrogens present in this particular borane. Okay, so diborane 6, this is hexaborane 10, this 10 is number of hydrogens, decaborane 14, this one pentaborane 9, and this one is octaborane 12. Octaborane 12. Okay, so these are the numbers which indicate the number of hydrogen atoms present in that particular borane. Okay, now next one, hydroboranes. Simple boranes and hydroboranes. Hydroboranes are the compounds which have molecular formula equivalent to BnHn plus 6. So simple boranes, they have BnHn plus 4. Here hydroboranes, they have the formula BnHn plus 6, where N is equal to 4, 5, 6, 9 and 10. So these are called hydroboranes. Now these are unstable and they have low melting points. These are unstable, whereas simple boranes are stable. And here these are unstable and they have low melting points. Now let's consider the examples. The first one is B4 H4 plus 6, that is H10, B4 H10. So this is 4 tetraborane 10. 10 stands for number of hydrogens present here. Here B6 H12, hexaborane 12. Here B10 H16, decaborane 16. Decaborane 16. And this one pentaborane 11. This one is enneaborane 9. Enneaborane 15. 15 stands for number of hydrogens present here. So, among the numerous boranes, diborane, that is the first member of simple boranes, B2H6 is the most extensive studied and hence discussed here. So, most of the other boranes are prepared from diborane only. So, diborane is the first member of simple borane series, and this is extensively studied, and this is used as a starting material for many other boranes. Now, let's study about diborane. Okay, so diborane is B2H6. B2H6. It comes under the general formula BnHn plus 4. Okay. Now let's see the preparation of diborane. So preparation, it is the simplest of the hydrates of boron. Hydrates of boron, it should be boron, and can be prepared by the different methods. The first method, let us consider. Here, it is obtained by passing silent electric discharge through a mixture of boron, trichloride and hydrogen at a low pressure. So silent electric discharge is passed through a mixture of boron, trichloride and hydrogen gases at low pressure. Okay, so 2BCl3 plus 6H2. Here electric discharge is passed, then we get diborane, that is B2H6, and other product obtained is HCl. Product obtained is HCl. This is the first method. First method where diborane is obtained from BCl3 and hydrogen. Next one is by the reduction of boron trichloride with lithium aluminum hydride. So this is reduction of BCl3 with lithium aluminum hydride, a reducing agent. So here let us see the reaction. BCl3 plus LiAlH4 lithium aluminum hydride gives rise to B2H6 plus AlCl3 plus lithium chloride LiCl. So to balance the equation here, 4BCl3 plus 3 lithium aluminum hydride gives rise to 2 moles of diborane plus 3 moles of AlCl3 and 3 moles of LiCl. So these are the two preparations from BCl3. One is from BCl3 and H2, other one is from BCl3 and lithium aluminum hydride reduction. Now third preparation, let's see. Third preparation, by reducing gaseous boron trifluoride that is BF3, with sodium hydride at 180 degrees centigrade. At 180 degrees centigrade, BF3, that is boron trifluoride, is reduced with sodium hydride NaH to give B2H6, and other product obtained is sodium fluoride NaF. So BF3 plus NaH gives rise to B2H6 plus NaF. Okay. Now next preparation is by treating magnesium boride Mg3B2 with hydrochloric acid and phosphoric acid. The reaction gives a gaseous mixture of boranes. Upon heating the mixture boranes, they form diborane. Now let us see. This is magnesium boride Mg3B2. It is treated with hydrochloric acid or phosphoric acid. Here we are considering phosphoric acid H3PO4. Then we get mixture of boranes. We have studied number of boranes. Okay, so mixture of boranes are obtained. This mixture of boranes, on heating, it gives diborane. So diborane is obtained upon heating this mixture of diboranes. Okay. So these are the four preparations of diborane. Now let's consider the properties of diborane. Properties of diborane. So diborane is a colorless gas with the foul smell, that is bad smell, and it is extremely toxic, and it is stable only at low temperatures. When heated at high temperature, diborane may be converted into other boranes. At high temperature, diborane becomes, or it gives, other higher boranes. Okay. Now here we can see B2H6 upon heating to high temperatures, 100 degrees centigrade, 180 degrees centigrade. Then what happens? It gives B4, that is tetraborane B4H10. This on heating to 95 degrees centigrade, it becomes B4H14, B10H14, that is decaborane 14. So when this is heated to 60 degrees centigrade, we get this pentaborane 11. Pentaborane 11. So this on heating to 120 degrees centigrade also, it gives this pentaborane 11. Now this is heated to 180 degrees centigrade, it gives B10H14, that is decaborane 14. On heating to 180 degrees centigrade, it can also give B5H9, that is pentaborane 9. So like this diborane on heating to different temperatures, it gives different other boranes, higher boranes. So this is one of the properties of borane. So it is stable only at low temperatures. At high temperatures, it gets converted to other boranes. Next one, action of oxygen. This diborane, when it is burnt in presence of oxygen, when it is burnt in presence of oxygen, it forms B2O3 and liberating heat, evolution of much heat. Because of that reason, it is used as a rocket fuel. It is used as a rocket fuel because on burning in presence of oxygen, it explodes, it liberates a lot of heat energy. Because of that reason, it is used as a rocket fuel. Okay. Next one is hydrolysis. Hydrolysis. So boron hydrides are hydrolyzed by water, forming boric acid and hydrogen. So when this diborane, it is hydrolyzed, that is add water and heat it. Okay, then what happens? It forms boric acid, that is H3BO3, liberating hydrogen gas. The rate of hydrolysis reaction, it depends upon the nature of the borane. So which borane we have considered, based on the rate of this particular reaction depends. Okay, next. Action of alkali. Action of alkali. Boranes, when treated with alkalis, that is bases, form hypoborates. They form hypoborates. Okay, so now let us consider this B2H6. When it is treated with KOH, that is potassium hydroxide, okay, aqueous solution, then we get potassium metaborate KBO2, liberating hydrogen gas. Similarly, if we consider this tetraborane 10 treated with KOH, we get potassium hypoborate. Potassium hypoborate, KOBH2, liberating hydrogen gas. So this is action with alkali. Now next one is action with ammonia. Action with ammonia. Then diborane, it reacts with ammonia to form different products depending upon the condition. So based on the quantity of ammonia taken and based on that temperature, we get different products. So diborane, when it is treated with ammonia, that is when ammonia is excess and the reaction is at low, taking place at low temperature, then we get diammoniate of diborane, that is B2H6 2NH3 is obtained. Okay. Now if the reaction is taking place at a high temperature, that is at about 200 degrees centigrade with excess of ammonia, this diborane, it gives this particular compound, that is B3N3H6, liberating hydrogen gas, and this is known as B3N3H6 is known as borazole or borazine. It is known as borazole or borazine, and it is also called inorganic benzene because it resembles benzene in its structure. So B3N3H6 is known as inorganic benzene. We know benzene is C6H6. Okay, so say, even this compound, it has similar structure like that of benzene. Because of that reason, it is called inorganic benzene. So this is borazole, or it can also be known as borazine, Z-I-N-E, zine. Okay, so this is one reaction. And next one, at high temperature and excess of ammonia, this diborane, it combines with the ammonia to give boron nitride, Bn taken X. Okay, boron nitride is obtained. So based on the conditions, different products are obtained when diborane combines with ammonia. Next one, action of halogens. Chlorine, generally, it reacts violently with all boranes except decaborane to give boron trichloride and hydrogen chloride. Boron trichloride and HCl are the products obtained. So decaborane, it reacts slowly with chlorinated room temperature to yield monochloro and dichlorodecaboranes. Okay. Now here, let us see. This is diborane, reacts with chlorine to form B2H5Cl plus HCl. That is, one hydrogen is replaced by chlorine. Okay. Now here, next reaction, with excess of chlorine, we get BCl3 and H2. With excess of chlorine, BCl3 and H2. And with excess of chlorine, it can also give BCl3 and HCl. BCl3 and HCl, that is boron trichloride and hydrogen chloride, are obtained. Okay. So if we consider this decaborane, okay, it forms mono and dichlorodecaboranes. You can see here. Monochlorodecaborane, this is dichlorodecaborane. Okay, so decaborane, it combines with chlorine to form mono and dichlorodecaboranes. Whereas diborane, it gave BCl3 and HCl. Okay, next. Structure and bonding in diborane. So let's discuss the structure of diborane. Okay. Electron diffraction study shows that some B2H6 molecule contains two coplanar BH2 groups. Two BH2 groups, coplanar BH2 groups are present in diborane. So the remaining two hydrogen atoms, they lie centrally above and below the plane linking the BH2 groups and hinder rotation between the two boron atoms. Now that is about the electron diffraction study of diborane molecule. Okay. Now let us discuss about this. So B2H6 molecule, it contains four 2-center 2-electron bonds. These are normal bonds. And two 3-center 2-electron bonds. These are the special bonds, which are also known as banana bonds or tau bonds. Okay. So these four bonds are normal bonds, 2-centered 2-electron bonds. Whereas here These are the special bonds. There are two special bonds which are known as three-centered two electron center in the sense atom. Three-centered two electron bonds which are special bonds which are called banana bond or tau bonds. Okay. Now let's discuss about the structure of this diborane from based on this electronic configuration. So now ground state electronic configuration of boron atom, if we consider, we know that it is 1s2, 2s2, 2p5, 2p1, altogether 5 electrons. 1s2, 2s2, 2p1. Now in this state it can form only one bond because it has only one unpaired electron in the ground state. In the excited state, if we consider, this electron is promoted to one of the p orbitals. You can see here, this electron is promoted to one of the p orbitals. Now it has in the excited state three unpaired electrons. Thus it can form three bonds. Now in this state, this boron atom, it undergoes sp3 hybridization. sp3 hybridization. One s orbital, that is outer shell s orbital. This is 2s orbital. And three, these three arrow should be up to here. Okay, so s orbital and three p orbitals, one s orbital and three p orbitals, sp3. So sp3 hybridization, it undergoes in the excited state. So out of the four orbitals produced due to sp3 hybridization, three orbitals they have unpaired electrons and one orbital is vacant. Now let me show this. Okay, so here boron atom, it undergoes sp3 hybridization forming four sp3 hybrid orbitals. Out of the four, three are having unpaired electrons, one is vacant. Now in this, three are having unpaired electrons, one is vacant. Okay, and this is vacant orbital here, dotted line. Okay, so like this, it is four hybrid orbitals are formed from each boron atom. Now, three sp3 hybrid orbitals having let me say, these two sp3 hybrid orbitals on each boron atom, they overlap with s orbital of hydrogen to form BH2, like this, BH2. Okay, this is one BH2, this is another BH2. You can see here, this BH2 coplanar BH2 groups are present. Okay. Now, the remaining two hydrogen atoms, they lie above and below here. Okay. So, this hydrogen with one electron, it combines with vacant sp3 orbital of this boron, half-filled sp3 orbital of this boron to form a bond that is only known as three centers, 1, 2, and 3. Three-centered, two electron bond. Only two electrons are there. One is of hydrogen and another is of this particular boron. Now, if we consider this bond, three-centered, two boron atoms, one hydrogen. And only two electrons. One electron is from hydrogen and another electron is from this particular boron. Because this boron is participating without any electron. This sp3 orbital of this particular boron participates in this overlapping without any electron. This has one electron, this has one electron, and it has no electron. So this is known as three-centered two electron bonds. Such type of two bonds are present. Three-centered two electron bonds are two. And this is one BH2 group, this is another BH2 group. So we can see the structure here. So BH2, and this is BHB bond. This is known as banana bond or tau bond or three-centered two electron bonds. And these are the different parameters. That is bond lengths, 119 picometer, this one. And this bond angle is 120 degrees. And this angle is BHB bond angle is 83 degrees. And this one is HBH is 120 degrees. And this is BH bond length, that is 131 picometers, this center. And this BH bond length and all these BH bond lengths are 119 picometers. Okay. So this is banana bond. This is known as banana bond, BHB bond, three center two electron bond or banana bond. Such type of two bonds are present in diborane molecule. Okay. So here hybridization we have to remember. The two boron atoms of diborane molecule, they undergo sp3 hybridization and give four sp3 hybrid orbitals in which three orbitals are singly filled, that is half filled, one electron they have, and the remaining orbitals are vacant. These orbitals are arranged around the boron atom in tetrahedral manner due to sp3 hybridization. Now, Two sp3 hybrid orbitals of each boron atom overlap with the s orbitals of two hydrogen atoms and forms two center two electron bonds. These are the common bonds, and that is two electrons are concentrated between the two atoms are nuclei. So that is known as two center two electron bond, and these bonds are equal to simple covalent bonds. The hydrogen atoms which are bonded with the two center two electrons are known as terminal hydrogens. Terminal hydrogens. Now I'll show you. So these are terminal hydrogens. These are terminal hydrogens. So there are four terminal hydrogens. This BH2, this BH2, four terminal hydrogens are present. And okay, next. Two sp3 hybrid orbitals of each boron atom. They overlap with s orbitals of two hydrogen atoms and they form two center two electron bonds. We said these are the normal bonds, common simple covalent bonds, and the hydrogen atoms which are bonded with two center two electrons are known as terminal hydrogen atoms. Okay. Now, the vacant sp3 hybrid orbital of one boron atom and half-filled or singly filled sp3 hybrid orbital of second boron atom and s orbital of hydrogen atom are combined to give three-centered two-electron bond. Three-centered two-electron bond. Okay, and that is two electrons are localized between the three centers, and that is three atoms. And singly filled sp3 hybrid orbital of b1 atom, vacant sp3 orbital of b2 atom, and s orbital of hydrogen atom overlaps to form another three-centered two-electron bond. And the hydrogen atoms which are bonded with three-centered two-electron bond are called bridged hydrogen atoms. I'll show you where the bridged hydrogen atoms are present. This is one bridged hydrogen atom. This is another bridged hydrogen atom. So one, two, three, four. These are terminal hydrogens, and this one and this one, these two are bridged hydrogen atoms. Okay. Now, bridged hydrogen atoms. Okay. So with this, uh, I'll conclude this topic and I'll catch you with another topic in the next video. Thank you once again.